All right, so last lecture we introduced this Deutsch-Jozsa algorithm or problem, and today we're going to go through the algorithm to solve that problem. And then if we have time, I'm going to introduce the Grover. I forget. I don't think there's an N. Grover? Grover? Yeah, Grover algorithm for quantum search. I'm gonna introduce it, but I'm not, and I don't think I'll get to proving it, and then next lecture we'll do proving it. So I still haven't made up my mind. Either next lecture or the one after that, we'll actually try to do a lab type of class where we actually try to implement the Grover algorithm for a search algorithm in the IBM quantum platform, so that we get some hands-on experience. I think I'll announce it if it's next lecture. I think it might be Monday. But in that case, I'm gonna split you up into groups, and you should be prepared. And hopefully one of you brings a laptop to work on the algorithms together. For preparation, you should sign up for the IBM Quantum platform, create an account, so that you can start coding. So let me just recap the problem that we have for this Deutsch-Jozsa algorithm. We have a function from 0 to 2n minus 1 with capital N, where I made this identification of little n and capital N, so 2n minus 1. And I'll be dividing by 2, so that's why I keep it as an even number. And it maps to 0 or 1, and the function is either going to be constant or balanced, meaning that it's going to take the value 0 or 1 an equal amount of times on the possible inputs. And the problem here is to determine an algorithm that tells you whether f is constant or balanced. So in here, this is where there's the error in the computation. Bless you. So in here, I was trying to motivate that classically to figure out this problem. It takes a lot of measurements, which in this case, a measurement is evaluating the function. And it takes a lot of measurements to figure out whether it's balanced or not, or constant. And the way that I set this up is by assuming that f is equally likely to be balanced or constant. And I was computing the probability, given k number of measurements, what's the probability that it's going to be balanced? And showing that to have probability either 0 or 1, you have to do capital N measurements, or 2n over 2. And there's a small issue in the computations here. Let me explain. And so in here, the first one is right. If I make one measurement, if I evaluate it at 0 and I get 0, I still don't know. I have nothing else to compare with. So since f is equally likely, it's 50% chance that it's constant and 50% chance that it's balanced. And then this is where my mistake started happening. What I really want to compute in here, what I really want to compute is probability that it's balanced given two measurements. I'm going to denote k is equal to 1. So in here, given that the probability that it's balanced given that for k equals to 1, I get that f0 up to fk, they're all the same. That it's constant for the k measurements, or the k plus 1 measurements. So this is what I want to compute. Given this measurements, what's the probability? And instead, what I've gone and done is compute for you what's the probability that we get k of those measurements, k equals 1, given that it's balanced. So I computed the opposite. So this is also k given that it's balanced. So in these computations, if I assume that it's balanced, what's the probability that I get constant measurements? So this is what I've computed, and using Bayes' theorem, I can actually compute the other probability. But in this case, we can actually see how we first, to compute Bayes' algorithm, first we need this computation. So if it's balanced, and I measure that f0 up to fk, they're all equal to each other, then that means that the first one was either 0 or 1, but it does not giving us any information. But the second one has to be the same as the previous one. And since we already measured it once, then you can only choose n minus 1 options that will give you the same measurement. So it's got to be n minus 1 over 2. And then for the third one, you have n minus 3 choices that will give you the same thing, the same constant measurement. So, and then you go up to n minus k. And the worst case scenario is that the first n values are all constant, and then it switches to not constant. And that's when, that's the worst case scenario in this procedure. And you can choose arbitrarily which numbers you want to measure, but at the end of the day, it doesn't matter. You can just relabel them. So I've been choosing 0 through k. So in that case, for that reason, there's a small probability that you're going to choose the worst case scenario. You're going to get the worst f possible, but you really need to do n plus 1, capital N plus 1 measurements to figure, well, actually, we just computed this. So, and to actually figure out what we want to do, we actually want to compute probability that it's balanced given k. So in here, after class, this is what I was discussing with Nyok, that how to actually like fix my computations using Bayes' algorithm. So that was our original discussion, and I cleaned it up. So what I really want to compute is probability that the function is balanced given k plus 1 consecutive constant values. And so I apply Bayes' theorem, and I flip the k and the balance. And in here, this is what I computed before. And so this is going to give me this value. And here I have also what I computed before this. It's going to be this. And our assumption here is that the probability of being balanced and constant is equally likely. So this is going to give me that this is 1/2, 1/2, and 1/2. So I can cancel all the 1/2s. So that's going to be, that's what, and here I don't carry the 1/2, so all these probabilities cancel out. And then the next is, given that the function is constant, the probability of having k plus 1 measurements that are constant. And if it's constant, the probability is going to be equal to 1. So I get a 1 right here. And in here, the main observation that I wanted to take away from this thought experiment is that when k is equal to n, meaning that we've done n plus 1 measurements, that's when the probability goes to 0, that it's balanced. So if we have n plus 1 measurements that are constant, then that's when the probability of being balanced diminishes, or it becomes 0. So in that case, that's when we know for sure. But the thing to observe is that you could, if you are fine with some error, you can just, the probability decreases exponentially, maybe faster than that. I make an error also in defining the complexity of, or the rate of things being exponential. And when I say exponential, I mean not polynomial, but there's different rates out there. So it's a catch-all term. So be careful when I say exponential. But in any case, it means fast. So, excuse me?
It looks like.
Yeah, that's why I just did that whole speech about me being wrong. Factorial, I think, is super exponential. That's what people call it. But this is another time when I quote Shakespeare, right? Or was by any other name still the same?
It's a lot.
Yeah. I don't like to memorize things. That's typically my MO, and so definitions often catch me off guard. I just kind of understand the concept and move forward. So it doesn't make it great when I'm trying to communicate to other people. So let that be a lesson. And then, of course, I wanted to save some face and say that what I said wasn't that wrong. So I make an additional observation that the actual probability that we were interested in computing was bounded by this quantity which I was computing. And my goal was to show that for k equals to n, the probability equals to 0, and I can show it with that bound. So I could retroactively claim that that was my original intention, but I just got lucky that that bound actually works out. But that's the main idea, that you're going to need a lot of measurements in this case to actually find out whether the equation is balanced or not. And with the quantum algorithm, we actually are going to figure out a way to do this with a lot less measurements to have a dramatic speed up. So this is a basic toy example, which has very little applications that I can think of, where you can have a dramatic speed up. But the catch is that there's no real application to this, and that's the catch with all quantum computing, that it's still unclear whether the speedups give you something that has a worthwhile application. But it's a proof of concept at the very least. Questions? Oh, what? What is this? Another round of Jeopardy? And it's worth 200? I'm claiming that the previous one was 100, so Forrest, you're at 100 right now.
I'll take that cash.
Yeah. At the end of the course, we'll all wager our money. So, definition. It's an adjective. 1, of lower or second class or rank, subordinate, subsidiary. 2, providing additional help or support, auxiliary, supplementary.
What is ancillary?
Yes, that's it. I'm still waiting for everyone to not phrase it in a question format, but you guys are too good. What is And ooh. Is that the correct spelling? All right.
That's against ciliary. I don't think there's missing.
One eye?
Yeah.
Ciliary? This one? All right.
Ciliary.
Ancillary. All right. So let's move on to the claim for the Deutsch-Jozsa algorithm. So in here, the claim is that this quantum circuit is going to spit out the answer. And I think this is if f is constant. And if and only if. So bless you. The claim here is that this quantum algorithm is gonna give you the if f is constant, the final state psi 3 is gonna be this state, specifically this state, with probability 1. And if it's not constant, it's not gonna be this state. So and I think it's gonna be with probability 0. So let's double check that. Let's keep that in mind, but I think it's gonna be 1 or 0. Gotta double check that. I know this is right. F constant, and F balanced. We gotta double check this when we go through the proof. But this is the claim. This is gonna give you the answer. And it's fewer steps. And here, to explain this quantum circuit a little bit more, these are n qubits. So in here, the input is going to be n qubits. So that means that the basis is going to be x1 through xn, and where each xi is either 0 or 1, and this is going to represent, each basis element is going to represent the binary expansion of a number. So it's going to be, x1 2 to the 0 plus x2 2 to the 1 plus x n 2 to the n minus 1. So this is giving me the set. The basis is going to be the set of the numbers. We can think of them from 0 to 2 to the n minus 1, which is my set 0 to 2n minus 1. So in here, the basis of this qubit, all these qubits represent all the possible inputs that f could take. And the identification is through a binary expansion of the numbers from 0 to 2n minus 1. And in here, we encode those possible inputs in the first n qubits. And the last qubit is 1 qubit. 1 qubit. And this qubit is called what? Ben?
What is ancillary?
That's not a question. Yeah, this is an ancillary qubit. So it's providing additional help or support to carry on our circuit. So, yeah.
The S and Z in Jozsa got reversed.
Which one is it?
I just looked up at Z first.
C is first? You looked it up?
Yeah. That's the other name.
C, S? Oh, no, the other one.
The S and Z in
That's-
Jozsa.
What's the origin of that name? Do you guys know? My hunch is that it's Hungarian. But
The guy's Australian.
Australian? That's close to Hungary. Oh, Australia. Oh my God.
They're right next to each other.
I mean, never mind. CS. All right. So non-Hungarian. Man. All right. See, I just want to hear that I'm right. So I was like, oh, that's why I heard Austria. So this is going to be an ancillary qubit, and the claim is that after we apply this quantum circuit, psi 3, it's either going to be in this state or not, depending whether f is constant or not. Any questions? So now what we're going to do is we're going to go through the circuit and compute the different psis. This one, and this one. Yes?
When we're doing there's n iterations of that first part.
Here?
Yeah.
So is the question from here or the question from here?
The first one.
This one. So the notation here means that it's n qubits. So typically if you have 2 qubits, you do 2 lines like this. 3 qubits, you do a line like this. But if you want to represent that for a general n, then you use this notation. And in particular, this means that it's 0, 0, 0, 0, 0. And in here, the book, I forget if it's here or later, that they, instead of using zeros and ones for the notation of that goes inside the ket, they put the number inside. They put a number from 0 to 2n minus 1. But you have this identification. So in here, since they put only one number 0, that means that all of these are 0. All of the x1s through xn are 0. And then in here we have an operator. So this is the Hadamard gate, which we worked with last class. And we have another operator here that takes the x and the f, and it passes x straight as the identity, and it takes y, and it transforms it to y plus f of x mod 2. So this is going to be either 0 or 1. And f can only be either 0 or 1. So, and y can either be 0 or 1. So it's just a mod 2 summation. And then we apply the Hadamard gate again. And really we're just interested in measuring what's happening here and forgetting about this, the ancillary. So this is going to be the first part that we're going to measure, and it's going to be all zeros. So let's go through computing the steps of the quantum circuit. So the action of the Hadamard gate on both bases, 0 and 1, just on that single qubit, it's going to be this 1, 1 or 1 minus 1. And this is what we defined before. And here, this gate is going to be the Hadamard gate on each qubit, which is 0, 0, 0, 0. So I'm applying this Hadamard gate on each one of these. And each one of these is 0, so each one of these is going to be this. So what I obtain is that after pulling out the factor of all the terms, I get 1 over square root of 2n. and each of these zeros gets transformed to 0 plus 1. And it's all of them. And then what I do is I distribute the tensor product. So I just distribute the tensor product, and since for each qubit I have 0 or 1 to choose from in the product, then what I end up doing is I end up creating all the sequences of zeros and ones in here. And this is just going to be a linear combination of all sequences of zeros and ones. So this xi, x1 through xn, each of them is going to be either 0 or 1. So in here we actually have 2 to the n terms. And xi could be either 0 or 1. So I create all the possible values, all the possible inputs for my function. And this is part of the trick to be where the quantum algorithm is faster than the classical algorithm, because essentially I can try all things at the same time, all possible inputs. Instead of measuring one at a time, this is going to be, once I create this state, I'm going to be able to measure all the possible inputs of the function at the same time. And this is what we're taking advantage of here is superposition of states. You can be in multiple states at the same time. So you can measure them all at the same time. So that's going to be the action of, on the first n qubits, I'm going to get this summation over all possible inputs. And then I'm also acting on this qubit with the Hadamard gate. And in this case, it's going to map it to 0 minus 1. And I pull out the overall factor, and then I have this. And here I don't distribute, I just leave it that way. I'm more interested in the summation of all the possible inputs, that they're equally weighted. Any questions? Does this make sense? So in here we've computed what psi1 is going to be. Now we wanted to do the computation for psi2. So in here, psi2, or in here, we already know what psi1 is, and we know what the qubits here are going to look like. And in here we know that these qubits are going to be mapped as the identity. Yes?
On the previous slide, it looks the normalization. You got square root of 2n plus 1 over there. Was that supposed to be the square root of 2 from the other ants, like qubit that got moved over, or did that come from somewhere else?
You're asking about this one?
Yes.
Yeah, so we have this, and then from the second one, from this one, we get this one too.
But still, it's just that one's still there.
Yeah. Yeah. I wrote it twice. Yeah, thanks. Nice catch. All right, is that good? Great. Oh, too many. So here, the action of UF, I map x to x. So nothing in the first n qubits is going to change. The only thing that's going to change is in the last qubit. And here, the last qubit is in the state 0 minus 1. And in here, if I apply the operator UF, then this is going to be my answer. If F is 0, then nothing's going to change. It's going to be 0 plus 0 and 1 plus 0. So it stays the same. If F is equal to 1, it's going to flip it. It's going to be 0 plus 1 is going to be 1, and 1 plus 0 is going to be, or 1 plus 1 is going to be 0, so it's going to be minus 1. So it's going to flip the order of the zeros and ones, and in particular, what it's doing is just changing the sign of this state. So if you, in here, it's not the sign stays the same, and here you're multiplying by minus 1. So if f of x is equal to 1, you multiply by minus 1. So in here, this is going to be the action of the UF operator. So I have xy, it's going to map it to xy times -1 to the f of x. If y is in this state. And in here, the choice of 0 minus 1 is important. And in here, we're using more than just a superposition of two states. We're actually doing a superposition with a twist from the phase of minus 1. If it was 0 plus 1, then the sign wouldn't change. And it would just stay the same. It would be the identity. But 0 minus 1, if you add this phase factor, the sign actually changes and the action is non-trivial. So this is something important that's also coming into play for this quantum algorithm. That's going to switch the sign of the state if f of x is equal to 1. Questions? All right. So psi 2, if we apply it to all of them, it's going to be this superposition where now different states are going to have different phases. And here, if f is constant, what's going to be the relative phase of all the states? Does that make sense, the question? What's the relative phase? So let's even make it a little bit simpler. Assume f of x is equal to 0 for all x's. What's going to be the phase in that case for each state? Yeah, -1 to the 0. So it's all the phases are going to be 1. And if f of x is constant and equal to 1, what's the phase of all states? Someone else that hasn't participated? What's this value when f of x is equal to 1? -1. And if it's constant, it's going to be -1 for all of them. So relatively, they're all going to have the same face. And so if it's constant, all the states are going to have the same face. And now what if it was balanced, meaning that it could be plus or minus 1? Then in that case, half the states are going to have face minus 1, and half the other states are going to have face plus 1. So the faces are going to start flipping. So that's going to create a different type of state. And that's what we're going to exploit. That we somehow try to capture the idea that in the constant case, everything has this same relative face. And in the balanced case, the face flips, alternates. And that's how we're going to be able to tell whether it's constant or balanced. So let's move on to psi 3. Oh, did I? So in here, we're now applying the Hadamard gate on the first n qubits. And in here, this is my claim. I did this one backwards. I wrote the answer and then I wrote the proof. My claim is that the action on a specific state, x, where x is equal to x1, x2, and xn, and z is going to be c1 through zn. The action on a specific state is going to be, again, a linear combination of all possible inputs, which I denote them by z. And the phase, in this case, is going to be minus 1 to the x dot z. And this is just the typical dot product. X dot z is equal to x1, c1 plus x2, z2 plus dot dot dot, xn, cn. So in here, the action of the Hadamard gate on any element is going to be given by this. Before, what we looked at before was this action when x was equal to 0, and this x dot c, 0 dot c was equal to 0, so the phase was all equal to 1. So it was just a linear combination of all possible states. So in here, you can actually see how the computation works. This action of the Hadamard gate, you apply component-wise, and depending whether xi is 0 or minus 1, introduces a phase in here. If it's x1 is equal to 1, then it's going to be a minus 1, and if x1 is equal to 0, it's going to be 1, so minus 1 to a 0. So in here, this is going to be the action on each of the qubits, and then you distribute the tensor product and if you keep track of the phase, then it's going to be equivalent to this dot product. And it's going to give you the action. It's going to be a linear combination of all possible states, and the phase is going to be depending on x. Questions? So, and here in the computation before, I did it for just as one element x, but in here, if we look at in here, the state that we have here is going to be a linear combination over all x's. So I need to apply h tensor n to this one. and then I move it inside the summation, and what I obtain is a summation over z and x. And I have the -1 to the f of x from this operation, and then the -1 to the x dot c from this operation. And psi of 3 is now this. Psi of 3 is now this linear combination. Questions? And of course, y is still 0 minus 1. Should probably make it normalized, but in any case. So this is the output. And now we again make the observation of what the phase is going to be. What the phase is going to be for either constant or balanced. So actually, the first thing to note is actually what I want to say is this: if z is equal to 0, 0, 0, and f is constant and f is balanced, the two cases, if z is equal to 0, 0, 0, then this is going to be equal to 0, and this is going to be constant, whatever constant value f is. And if f is balanced, this is going to be alternating between plus or minus 1. And now what I want to measure is the coefficient in front of the state 0, 0, 0. So in that case, this is actually, I think this is right. So I apply this bra on the left, and in here, this dot product, this bracket, is actually going to be it's going to be equal to, this is either going to be equal to 0 if c is not equal to 0, and it's going to be equal to y otherwise, if c is equal to 0. By taking the dot product, since these are orthonormal. So in here, I have that if f is constant, then this exponent is just going to be minus 1 to a constant. Should be minus 1 to a constant. So everything's going to sum up. And in the other case, 1 over 2 and square root of 2, it's going to be x minus 1 or plus or minus 1 times y, which is equal to 0. So in here, these are going to be 2 to the n terms with the same constant. And I can just factor out the y. And then 2 to the n is going to cancel out, and I'm just going to have this. And here, this y is also just constant. So I'm just summing plus or minus 1. And half the time is plus 1, and the other half is minus 1. So this is going to give me 0. So if f is constant, I'm going to output this state. And if f is balanced, I'm going to output 0. So when I mesh, and the thing to note now is that this term has norm equal to 1. And since the whole state has to be normalized to 1, then this is the whole component of the measurement. This is all psi 3 because the norm of this component is equal to 1, so the rest of the components cannot have any other norm because the probability would be greater than 1. So this is going to be a norm 1 component. So the measurement of psi 3 turns out that psi 3 is just 0, 0, 0, y. And then in this case, we see that the component of 0, 0, 0, y is going to be equal to 0. So in this case, we're able to tell and measure. And so in here, we see how using the Hadamard gate, we can look at all possible inputs at the same time. And additionally, we can use the Hadamard gate to actually change the phases to actually work in our advantage. And any questions? Does it make sense, the two computations at the end? All right. Yeah, the notation could be a little bit heavy with the summations, and it's easy to get confused, but this is the easiest example of, the most basic example of quantum speedup. One thing that I brushed over and needs to be shown is that this operator U of f is actually a unitary operator because our quantum states evolve according to unitary operators, and each of the gates has to be a unitary operator. In this case, it's just an exercise and it's not difficult to do. I'll let you think about it. And you have to show that U of f is unitary. And the first thing to show is that U squared is equal to the identity. And then show that the complex conjugate of U is equal to U. And then if you can show both these things, you have that it's unitary. All right, that's class. Yeah.